Hello and welcome to this video out of my networking basics series. I'm Wolfgang Tremmel from the DKIX Academy, and in this video I'm going to talk about modes of communication. If you're interested in more videos, in white papers or other downloadable content, just head over to the DKIX website where you can find interesting stuff for you to watch or download. So let's head over to the presentation. In this video, out of my networking basics series, I'm going to talk about Unicast, Broadcast, Multicast, and Anycast. This is all part of my networking basics series. I already talked about Ethernet, about IP, routing, TCP, UDP, and so on. Today, like I said, we are talking about types of communication. So, what are types of communication? Well, the simplest one is unicast, and unicast means one-to-one communication. We have one sender and we have one receiver, and they communicate with each other. Broadcast, that's like addressing a crowd. So we have one sender and he simply broadcasts his message to everybody. Multicast is addressing a group, so kind of a specialized broadcast. I'm not addressing all of the crowd, but I'm addressing part of it who has something in common. And the last one, Anycast, is, well, I'm addressing somewhere, but I really don't care who I'm addressing. So I'm sending my message, I'm sending it to one receiver, but I don't care who the receiver is. That's Anycast. So what does it have to do with the internet? What does it have to do with networking? So I talked about the internet model, about network layers working together. And these modes of communication, they happen on nearly all of the layers. Today, I'm going to focus on the link layer. So I'm going to talk about how Ethernet does that. I'm talking about the IP layer, about IPv4 and IPv6. And of course, I also talk about the transport layer, talking about TCP and UDP. Let's get started with the simplest mode of communication. Let's get started with unicast. Like I said, we have one sender and we have one receiver. And on the IP layer, that's the standard of communication for the internet. So we have an IP address, the sender IP address and the receiver IP address. The destination IP is the receiver, the source IP is the sender, and we have that in our IP packets, IPv4 and IPv6. The same is true for Ethernet. Here we have the destination MAC address for the receiver and the source MAC address for the sender. That's the standard when you send an email, when you get a picture, when you read a website. That's the unicast, is the standard mode of communication in the internet. Broadcast. Well, what's broadcast being used for? So it is often used for service discovery or for services provided by some network entities providing services. One example for broadcast is DHCP, and that's the protocol if your system joins a new network for getting an IPv4 address. DHCP stands for Dynamic Host Configuration Protocol, and it's the standard protocol in IPv4 to get an IPv4 address when joining a network. So your device joins a new network, broadcasts, I need an IP address, gets an answer from a server assigning that IP address. DHCP is based on UDP, and let's have a look at the network headers, at the IP header and the UDP header to see how that works. Well, The IP header we have here, adding also the UDP header. So this is the complete header of a packet. We have the source IP address and the destination IP and the source and the destination part. I'm not talking about the details in the DHCP data in this video. That would be the topic for a complete separate video. So DHCP, what do we put into the header? The source port is 68, the destination port is 67. That's always true for DHCP. But we do not have an IPv4 address yet, so what can we put in as a source IP? Well, we simply put in 4 zeros as a placeholder. And we want to broadcast that packet. So we need to put in a broadcast address as the destination IPv4 address. And the generic broadcast address for IPv4 is 4 times 255. So all bits set to 1. The broadcast address in general in IPv4 is the highest address of a network. Well, in case we are joining a new network, we do not know the network address, so we are putting in 4 times 255. If we do know the network address, well, simply we are setting all the host part, all the bits in the host part, setting it to 1, like here in this example. That's very easy. Simply set all the bits to 1 in the host part. That's the broadcast address. In my example with DHCP, we didn't know the network address, so we are setting all bits of the IPv4 address to 1 as the generic broadcast address. So, but how do we put that into an Ethernet frame? You remember encapsulating packets into Ethernet frames. So we have this IP packet with the destination IP set to 1, and we now want to send it in an Ethernet frame. So let's put it into the Ethernet frame here as a payload, and we need to fill out the remaining fields of Ethernet. So the Ether type, that's quite easy. That's OX800, that means IPv4. The source MAC address, that's also easy because that's the MAC address of our hardware, of our network card. We do not know the destination MAC address, as we also do not know the destination IP. Remember, the destination IP is the broadcast address. And Ethernet also has a concept of broadcast. And the broadcast address for Ethernet is all bits to 1. So 6 times FF in hexadecimal, all bits to 1. That's the broadcast address for Ethernet. And that means, dear switch, dear network cards, please send this Ethernet frame to all devices connected to the switch, to the network. So Ethernet frames with a broadcast address are forwarded to the CPU and to operating system for processing of all stations which are received. You can imagine why this can become a problem if the broadcast rate on any network is too high. How does the system know how to process this packet? Well, that's in the IP header and in the UDP header. For DHCP, if the receiving system has a UDP service running on port 67, it is processing the packet. The DHCP is processed and may be also answered. If there is no service running on that UDP port, this packet is simply discarded, but it still consumes CPU cycles on every connected device. And that might become a problem on large networks. At DKIX in Frankfurt, currently we have more than 1,500 stations connected, and we have more than 1.5 megabit per second of broadcast traffic. So this is We are not doing, of course, not doing DHCP on the DKIX network, but it still can be a problem on large networks. Conclusion about broadcasting. Broadcast means send to every device on a shared network. On IPv4, the broadcast address is the highest address in the network, so the host part of the IP address is all ones. And if you do not know the network address, simply set all bits to 1. Ethernet also has a concept of broadcast. Here we also have a broadcast address, and that's also all bits set to 1. IPv6 does not have a concept of broadcast. In IPv6, we are using multicast instead, talking about this later in this presentation. And you should avoid, if you are a software developer and programming applications, you should avoid broadcast whenever possible. So, next one. Next mode of communication, multicast. And remember, I just said IPv6 has no concept of broadcast. It was decided that, well, multicast is just a special case of broadcast, so that we do not really need broadcast. We can do everything we need with multicast. Remember, multicast is addressing a group of hosts, a group of systems instead of all systems. A group of systems can be something like all routers, or all interactive devices, or all network time protocol servers, or even more specialized, all routers running a specific protocols. And systems join these multicast groups when they run the protocol, when they are a router. And as an example, I will show you how neighbor discovery is used, works in IPv6. Neighbor discovery means discovering who else is on the local network. Like I'm asking, is there any router on this network? So this is how it works. A system asks, is any router here? Please make yourself known. And the router answers, hey, I'm a router, and the prefix here on this network is an IPv6 prefix. And that's how network address assignment in IPv6 work. There is no need to broadcast to every system. We are just asking the routers, and they have joined a specific multicast group. And let me show you how that works in terms of network packets, in terms of IPv6 headers. So we're just covering the IPv6 header part. We are not talking too much about how address assignment works. Neighbor discovery works using ICMP. I have made a separate video how ICMP works. If you have not watched it, please go back, watch the video about ICMP, which gives you some more details about this protocol. So this is an ICMP version 6 packet, and we need to put in source address. We don't have that yet. And we need to put in a destination address. And instead of the broadcast address, like in IPv4, we put in a destination multicast address. There is a list of possible multicast addresses. It's written in the documentation of IPv6 in an RFC, and all routers is address FFO2:2. So that means please send this IPv6 packet to all routers. Source address, well, like I don't have a specific source address, but IPv6 has the concept of so-called link local addresses. We are putting in the link local address of the sending interface. And the link local address is directly calculated from the MAC address. So we have that. We have a MAC address, and so we can calculate and put in a link local address. And again, we need to put that into an Ethernet frame, and there is also an RFC how to do that. Unlike IPv4, like I said, we are not doing a broadcast here, we're doing a multicast. The IPv6 packet again goes into the payload. We are setting the Ether type to IP version 6. The source address is again the hardware address of my network interface, and the destination MAC address, that's built from the multicast address. So the first two octets are 3333, and the last four octets of the destination MAC address are the last four octets of the destination IPv4. Remember what our IPv6 multicast address was. It was FF02:02. So we are putting this number 2 also in the destination MAC address. I know that sounds complicated, but it's all done by your computer. You don't have to worry about it. It's just to tell you how it works. We are not doing a broadcast. We are doing a multicast here, and the Ethernet destination MAC address is built from the destination IPv6 multicast address. So perhaps you want to know your computer you're just using, did it join any multicast group? Well, there is a number of commands for that. You can just type it in and can have a look which multicast group your computers have joined. Next mode of communication I'm talking about here is Anycast. Anycast is addressing one in a group. I don't care who I'm addressing, I just want my question answered. And unlike multicast, I'm not addressing multiple systems, I'm addressing only one system. So it's kind of unicast, but not really. So let me give you some more details. For the sender, really it is the same as unicast. I'm sending out an IP packet, a network packet, but I don't care who answered that. Why I don't care? Because everybody would give me the same answer. That's what I'm assuming. How to use that? What's the application of that? Well, one application, quite obvious, is the name resolution, DNS, getting the IP address of a network name. So I don't care who answers this DNS request, because the answer will always be the same. I'm sending out one packet and get one packet back. I don't care where this packet comes from. And UDP is in this case being used because UDP is stateless. There is no follow-up conversation. So I'm sending out a request for an IP address. I get an answer back, and I don't care where it came from. So how does it work in practice? How can Anycast being implemented? Well, the thing is, and this might come as a surprise because you are used to the fact that every IP address in the global internet is unique. In this case, it is not. We're using the same IP address at multiple places in multiple systems, even more than like here shown on the map. Also, we are using it with the same autonomous system number. If you have watched the global routing video, you know what it is. If you don't know what it is, it doesn't really matter. Because of that, the routing in the internet makes simply sure that the nearest system is reached and answers the query. So I'm sending out a packet to an destination system. I put in a destination IP address, but this IP address exists multiple times. I'm asking the question and somebody answers. If I'm asking the question here, I get the nearest system. If I ask a question here down in Australia, I also get the nearest system to answer. So why is this being done? Well, the answer is obvious: to keep latency low. This is the reason we are using Anycast for DNS, and that's the standard today how DNS works. It uses Anycast, multiple systems with the same IP address all over the world. Would it also work with TCP? Well, using Anycast with UDP is easy. There is no follow-up conversation. I'm sending out a packet, I'm getting a packet back. But you're a bit surprised. Well, it also works with TCP. Simply, the nearest server takes the TCP connection, and if anything happens to it, well, another server takes over. You would have to start over again, but you might not even notice it. Think of a website with a lot of pictures on it. If in the middle of transfer the server gives up, well, simply another server with the same IP address would take over. The TCP session resets and gets reestablished. The gain you have for lower latency really outweighs the occasional hiccup when there is a disruption or a rerouting. Conclusion. We talked about modes of communication today. We started with Unicast, which is the standard communication in the internet. One sender, one receiver, one-to-one communication. Broadcast, that's addressing a crowd. One sender, everybody is receiving. And that's most often used in Ethernet, in local area networks for discovery of services, of IP addresses, and so on. Multicast, that's addressing a group with something in common, like addressing all routers in the local network. Also used for joining a network in IP version 6. And Anycast is like Unicast, a one-to-one communication, but I really do not care who answers. And this is used to improve speed or to increase redundancy. And that's it for today with this video. Thanks for listening today, and I hope you join me again in my other videos. I'm Wolfgang Dremmel. I run the DKIX Academy. Thank you and bye-bye.